Segerman, and he's also worked in conjunction with the Hart, Andrea Hawksley, Elisabetta, Matsumoto, if I'm getting all these names right, Matsumoto from Georgia Institute, and Henry Segerman, he's from Oklahoma State University, and he is going to speak to us on using quaternions to color the cells of tiling of H3.
So this is what this project was about was virtual reality, and it would help if I plug this thing into my laptop so that it works. There we go. So before we get started, you can do this on your phone right now. If you have a phone that has a gyroscope in it, so maybe a recent iPhone should be able to do it, you just go to h3.hypernom.com. That's hyper as in hyperbolic and nom as in nom.com, and then on the web browser you can just play around with this and turn it around and you'll see what this is. Here I'm just going to show you what the thing is. So this is me wearing a virtual reality headset, and I'm exploring a hyperbolic space. And, well, as you'll see, I've got a sort of grid on the floor here, and there's a square here on the floor, and I'm actually walking around the four corners of that square. And I don't get back to where I started until I've actually traversed through 6 90-degree turns, because this is actually a right-angled hexagon in hyperbolic space. Okay, so this is visualizing hyperbolic space from the inside rather than from the outside. So often you see pictures like the Poincare disk model, or the Poincare ball model of viewing hyperbolic space. And the idea here is that you see geodesics, and that allows you to produce a simulation. This is not new. There's a lot of previous work, not video you might have seen this by Charlie Gunn and others at Geometry Center. Hyperspace is an application you can get for your laptop, which will do this. Let me actually just see if we can get out of this and show you. I'm going to be able to do this. There was a problem with switching to that. Let me mirror the displays. There we go. So this is what it looks like if you go to h3.hypernom.com on your computer, and you can use the keyboard to sort of fly around and see. And what I'm going to be talking about eventually is the coloring of this this lattice of cubes, and that's the bit that uses quaternions. Okay, so how do you implement such a simulation of, in this case, hyperbolic space? So there's 4 things that you need. So you need a computer model of the space. So you need some way to talk about points in the space, in this case, 3-dimensional hyperbolic space. You need a way to draw those points on the screen somehow. You have to be able to move around in that space. The headset that I was wearing in that video, it tracks your position in space, and you need to translate, or I guess, there needs to be a corresponding movement in the hyperbolic space that takes you around. And then if you just had a blank screen with black things, and I told you you were moving about in hyperbolic space, you wouldn't be impressed. So you need some sort of landmarks, something to see. So I'm going to spend a little bit of time talking about these different things. I won't go into too much depth, but how did we create the simulation? And then this set of landmarks, that's going to be this pattern of cubes, and the coloring I'll get into how quaternions use that. So the model, so there are lots of different models of hyperbolic space. The Poincare disk model is maybe the most familiar one. That's the Escher pictures, things like that. Klein model, and the one we actually used is called the hyperboloid model. You draw a hyperboloid in Kapsky space. This is the for 3-dimensional hyperbolic space. If you do 2-dimensional hyperbolic space, you lose this term here. So you have this hyperboloid, and it turns out that that's the most computationally efficient way for doing the rest of the things we want to do. So that was the first thing. What is the model of the space that we implement on a computer? The second thing, how do you draw objects in this hyperbolic space on the screen? So I mentioned before, you want to see along geodesics. That's sort of the way that you get inside of the space rather than just seeing some sort of map of the space from the outside. And this is sort of a schematic picture here if you're here and you say, what can I see if I look in this direction, you see a sort of cone out in front of you, and then you look at the objects that are in the way of that cone, and that's what you take these objects here and you push them back onto a little screen that you put in front of your eye, and that's what you see. And you can do the same thing over here. This is the Poincare disk model of H2, and one of the features of that is that the geodesics from the center go out looking like straight lines in Euclidean space. Of course, if I put my eye somewhere else and I cast a cone outwards, it would be curved in some way, at least in this model. What do you actually, how do you, so I mentioned sort of tracing geodesics back towards your eye. What we actually do is you take objects out in three-dimensional hyperbolic space, and you need to pull them back along geodesics to the tangent space to hyperbolic space where you are. And we actually draw things in the tangent space. This is nice and Euclidean, graphics cards like Euclidean things. This is a cube. The cube model we actually use was designed in a Euclidean a Euclidean 3D design program. It's difficult to come across hyperbolic 3D design programs. But then we sort of project that up onto the hyperboloid, and then we pull it back to the tangent space using the inverse of the exponential map. Maybe I'm going to say something about this. Oh yeah, maybe not. So then I need a way to move. This is one of my collaborators, Elisabetta Matsumoto, wearing a VR headset on the top of a building somewhere. It was sort of for a photo shoot or something. So what happens with this is you have this headset on, and there are sort of sensors that you put up in the corners of your room, and as you move your head, it's continually recording where your head is and what its orientation is and so on. So every frame of the simulation, we get a vector from the VR system that says you move by this amount in this frame, in this 90th of a second or whatever it is. And so here, suppose that vector is dx, dy, dz. This is sort of the instantaneous movement of your head in that frame. And then what you need to do is exponentiate that to get a matrix that you move yourself by within the simulation. So we take the Euclidean tangent vector and we convert it into a hyperbolic tangent vector to decide where you move. And, well, there's some details here I won't go into, but it turns out you can do this pretty efficiently. Okay, and now finally, what do you draw on the screen? So now we're getting a little bit closer to the things that I was talking about. So we're going to draw a tiling by cubes. So this is a Schlafly symbol, if you've seen these before. If not, I'll explain what it means. Actually, there were some of these a little earlier. Here, this is a two-dimensional Schlafly symbol. So this is a very efficient way to talk about certain very symmetrical tilings. So this one here is the 4-4 tiling. What that means, the first number tells you I'm going to make a thing out of squares, and the second number tells you how many of those squares go around each vertex. So if you take squares and you put 4 of them around each vertex, then you get the ordinary square grid. If instead you start with squares and you put 5 around each vertex, then you can't fit it inside of the Euclidean plane anymore. This is instead a tiling two-dimensional hyperbolic space. So what about when there's 3 numbers? When there's 3 numbers, the first 2 tell you I'm going to make a thing out of squares, same as before, and I'm going to put 3 around each vertex. So if you do that, you get a cube. But then those are the cells that you tile the next level up. So the 6 here tells me I want to tile 6 cubes around each edge. So it's a little hard to see what that looks like. So this is just 1 cube. And I'm going to layer cubes onto the outside. So there I've stuck a cube onto each of the 6 faces of the original cube. And then I put more cubes onto those faces, and you can see there's a little gap here. So if you just look at this edge, I've got 1 cube around it, I've got 3 cubes around it, and you can't see the edge anymore because there's 3 cubes out to 180 degrees. Now I've got 5 cubes around it, and the 6th one would go in there. As you can see, it's sort of difficult to draw pictures of this thing, comprehensible. So I made a 3D print. This may not be helpful at this range, but this is half of the Poincare ball model of three-dimensional hyperbolic space. And if you hold your eye precisely at the origin and you look around, then you should see, because in the Poincare ball model, if you look at geodesics that start at the origin, they're straight lines in Euclidean space, otherwise known as light rays. So if you can focus this near, which I doubt you can, then you should be able to see what is in the simulation. Okay, so actually, I guess now that I've told you about all these things, let me just go over here again so that we can sort of understand what's going on a little bit more. So this is the simulation. It just runs on a web browser. And as you can see, I've got these many colored cubes that are all over the place. And you can move around and see these different... so I think the 3D print there is what you see if you're just on the edge of one of these square faces. Actually, it's an octagonal face because I've truncated the cubes. I've cut off the corners. Okay, so let me go back to this. So, okay, so now what about the color scheme? So when we first did this, we just had lots of cubes, and they were all the same color, and it was super confusing. And you can't tell what you did, and you can't tell where you moved, because everything looks the same, and it gets very confusing. So we needed to come up with a color scheme, and how did we do that? So this is the color scheme we came up with, and where did this come from? So rather than looking at the coloring of this 436 tiling of three-dimensional hyperbolic space, let's talk about a color scheme for a hypercube. So a hypercube has 8 cubical cells, and you've maybe seen that sort of Dali's hypercubus picture. This is sort of another, the lighting isn't so great here. This is sort of another way of looking at this. So I've got 1 cube in the middle, and then 6 cubes arranged around that central cube, and then there's a cube on the outside, and this is the picture sort of from the inverted picture. So the middle cube in here is dark gray or black, and here the outer cube is black. Well, I've got a cube, I've got a hypercube sitting in 4-dimensional space. How do I relate that to Quaternions? Well, Quaternions have 4 elements. What I can do is I can take my hypercube, which is some polytope, and I can radially project it onto the unit sphere in the 4-dimensional space. And then the unit sphere are all nice unit Quaternions. I can view them as unit Quaternions. And here I've just made some sort of assignment between the 8, what would you call these? Canonical, cardinal direction unit Quaternions, and 8 colors. There is actually a meaning to these, but let's just, for now, I've got these 8 different unit Quaternions, and those are the centers of the 8 cubes of the hypercube. Where does this coloring come from? Because I needed to code this up, and I don't want to write lists of things saying, which Quaternion are you? Okay, you'd be red. I want a function. So let me show you what the function looks like. So this is the list again. So I've got these Quaternions. Well, the first thing, which is maybe not so obvious why I want to do this, is I take my Quaternion, which is one of these things, and I multiply it by -12 times this Quaternion here. What that does is it sort of rotates every point a little bit to put it in a nice position. And then we stereographically project from the point at the, I guess, where are we projecting from? We're projecting from the point W equals 1, so the real part is 1. So that means that if I just plug in 1 into this stereographic projection map, it will map to infinity. Everything else will map to something finite. And the reason that we do this sort of rotation first is that these 8 points end up all being arranged in this nice sort of at the corners of a cube and not getting sent infinitely far away. And the reason that I'm interested in that is because then I've got these points. I'm going to normalize them. So I'm in R3. I'm going to take all of those vectors and make them length 1. And so then I've got a 2-dimensional sphere, and then I can fit that 2-dimensional sphere inside of the red, green, blue color cube. So once you've got a point that's inside of the color cube, you've given a color to it. And so if I pull back through all of these maps, then that color gets associated to that cube of the hypercube. Now, okay, why did I bother doing all of this stuff? I mean, yes, mathematically there's just a list of things here, but it turns out that if you're writing code, you want to just have a function to do it. And I think there's some interest here in converting from an arbitrary unit Quaternion into a color. This is not going to not going to work in general, unfortunately, because if you have things that blow up, then they're going to go outside of this cube. So this is not a fantastic way to do things in general. It's useful when you've just got your your 8 points. Let me make a quick aside to how do you get a good coloring scheme for any unit quaternion. And so here's a scheme that's better in some ways. You take the unit quaternions, you view them as the 3-sphere, you map via the Hopf vibration to the 2-sphere, and then from the 2-sphere you put it inside the red-green color cube, red-green-blue color cube again, and you win. And so monkeys.hypernom.com, that was another project that we worked on that uses that. So let's go to this one. Thanks. So this is stereographically projecting a pattern of, well, a sculpture that lives in the 3-sphere down to R3, where the colors are colored according to this Hopf vibration way of doing things. The disadvantage with this, for my purposes, is that in the Hopf vibration, a quaternion and its negative get the same color. So that would mean that I don't get 8 different colors, I only get 4. So I didn't want to do that, I needed to do something else. Okay, so back on track. I've got this coloring of the hypercube. The hypercube is 4-3-3 in this Schlafly symbol way of doing things. 4-3 again is a cube. And if you fit 3 cubes around each edge, you get a hypercube. And this tiling that I want to color, I have 6 cubes around each edge. So you can lift the coloring from the hypercube up to this tiling of H3, and everything works out consistently. And maybe you can see here, so let's look at this edge here. There are 6 cubes around that edge, and if you go 3 cubes around, you're back to the same color, because you're back to the same place on the hypercube. So I think it goes red, black around the back, then blue, red, black again, blue, and that's going to work. And that's going to work everywhere, and it's going to be relatively simple to implement, and that's why we did it. There's a lot more I could say about how the implementation actually works. We have to build a tiling of this, we have to build a subset of this tiling out into space. I can't, unfortunately, my graphics card won't allow me to put down infinitely many cubes, so I have to go out only so far. And then as I move out, I've got sort of words in transformations in hyperbolic space to move around. And I associate with each of those words, I don't know why it keeps bugging out. I associate with each of those words a quaternion, and then products of those quaternions give me the coloring. In the last few minutes, there's another view. If I remove the edges, so this is removing the edges of the cubes, I've just got these truncated ends. You can fit, this is a sculpture involving monkeys, with a monkey in each cube of this tiling, and this is showing the twisting sort of relationship you have to do with the orientations of the cubes in order to get the colorings to work out. You can't just sort of translate forward and map the cube, map the colors of the cube appropriately. You have to translate forward with a twist in order to get it to work correctly with the quaternions, as in, well, this is not a coloring, this is another way of seeing the hypercube here. This is the hypercube with I, J, and K viewed as transformations of that hypercube with various twists of S3, which are the same as multiplication by quaternions acting on S3. And this is, I think I maybe don't have time to talk about this, but this is that sculpture again of monkeys, where the monkeys sort of give you an orientation that lets you see what is an I and what is a J and what is a K. So for example, there's a monkey in the middle, and if you go forward along its arm direction, then you get to this monkey, and that's the same thing as going here, so that's a multiplication by J, moves you forward in that direction. And then if you've got this monkey here, then again moving forward in the arm direction takes you around to the monkey that's at infinity in this picture over here. Last couple of minutes, there are some alternative colors, some alternate ways to do this. So this is the one that I showed you already. This is the lift of the hypercube coloring. Here's an easy color. You could just two-color. I just checkerboard. And then as we were coding this up, we made an error in, well, you know, there's an infinite number of binary choices, and you just keep flipping them around to figure out which is the right way to do it. And we came upon this coloring here, where this coloring has 6 colors around each edge, not 3. And we were very confused for a long time, but it works, so we left it in. And we now understand what is going on here. Well, what happened is that there's a list of quaternions associated to the various generators of my tiling, and you have minus signs on all of the quaternions from the 3-color version. And all that this is, we realize now, is a combination of this color and this color. Right, so this one, if you go halfway around the edge, you get back to the same color. This one, if you go halfway around the edge, black, white, black, white, you get to the opposite color. You just multiply them together and you get this thing, which we actually prefer, because it's sort of more interesting. And so I guess there's a question of what is there a hypercube here with a minus sign somewhere, or is there something else going on? Okay, I think I'm almost done. This is another picture of that 6 colors around each edge, and more monkeys and stuff. So thanks for your attention. I'll just switch this. If you are playing with this, then you can hit the C color the C key switches you between the different colors.
Okay.
And the number keys to
Who has the model? That the little. There we go. Okay. Just wanted to keep on track.
Any questions?
Okay. So, does anybody else?
Yeah.
Okay.
You also program this using virtual reality, using the headsets?
This is coded in, it's actually running on a web page. It's using something called WebVR, which is running on OpenGL, and it has hooks into the virtual reality substitute. So if you have the right headset and the right browser version, and it's a Tuesday, or then it may work for you. But it's sort of a difficult target to.
What headset do you use?
The HTC Vive.
Okay.
That's the top of the line one because it has positional tracking,
Right.
Which is really accurate and really not so nausea-inducing, which is really important. Yeah.
At a much more mundane level, if you're not using a headset, is it obvious how to move around?
On here, the arrow keys move you forward and backwards, and WASD rotate. Or if you're using a phone,
Phone would seem to work.
rotating, it works for rotation. It's slightly more obvious if you press and hold, then that moves you forwards. But it's not
Is there
as
instructions somewhere?
no, unfortunately not. Not very well documented. There's a paper. Maybe we'll start.
Thank you.
Research.
Thank you.
Yeah.
Is there an intuitive explanation for why the hot vibration plus or minus the percentage is the same color?
So let's see. So you can view the Hart vibration as you're in R4, but view that as C2, and it's just Z1 comma Z2, and the Hart vibration is Z1 divided by Z2. So if you negate both of those, nothing has happened.
So if you did some other exotic variable,
Some exotic map down to S2. Sure, you could get other things to happen. I haven't explored it.
Okay, any other questions for Henry? Anybody have any other questions? Going. Okay, gone. Okay, that was excellent.